Okay, last time we talked about finite state machine, and we designed a simple controller for a Coke machine or soft drink machine, and we determined hopefully towards the end that, I'm just curious what you're doing. Oh, okay. We determined at the end that we wanted something programmable so we could upgrade it depending on if the price changed or some other type of factors. What we're going to talk about here is going to be the initial, very, well, compared to what our processors are today, a very simple design for a general purpose processor or a central processor. And the best way to look about it is from the Datapath, namely how does data flow through the processor. So yeah, we talked about the vending machine, and we talked real quick about it was a mealy machine where you had inputs from the user as well as inputs from the state. Well, turns out that we're going to create what I call a little computer 64-bit processor. So that's what the LC64. You may see x86-64, you may see ARM. And this is another one that I'm using for this class, and I'm using my own because if we try and implement ARM or x86, no one would get their homework done. So we're going to just use a very simplified one, and I called it the LC64. But if we wanted to create our own processor as a finite state machine, well, the LC64 has 64 kilowords, or in other words, 64 to the 16 times 32 plus some extra inputs, which if you multiply all that out, 4 more bits in the universe. Not that number, but the total possible control lines from that decoder would be beyond the number of atoms in the universe, which is not useful. Because in other words, in order to make that decoder, the number of lines coming out is going to be 2 raised to this number, which is going to be obscenely huge. So we can't use a control ROM. That's not how it can work anymore. Because the other thing I forgot to mention is that in our processor, like most modern processors, you have your piece of memory and you have your register file. Well, memory y'all should be used to because it's RAM. It's what actually keeps it. Your register file, think of it as a very small scratch pad memory that's inside your processor to go do quick little tasks. But it's called a register file because we've seen a register, which is either an SR latch or a D flip-flop. A D flip-flop's a 1-bit register. Your register file is going to have multiple D flip-flop entries so you can reference different registers. Bless you. To show that I'm not just making it up, here's a good old Pentium processor die. Yeah, I know this is old, but the nice thing about older processors is it's a lot easier to identify what is what. So, your state, aka the current state of the machine, like the 2-bit we had in the coin machine. Here we're going to have registers and memory. Here's the registers, and here's the memory via cache. We haven't talked about cache, but just think about that as RAM that's on the processor. And we'll get to way more about cache later because it's very important. You have your control ROM, or in this case, you have decoding the instructions and complex instruction support. In other words, instead of having a decoder hooked up to tell you what's going to happen, we're going to have a circuit that takes an instruction and then dictates what needs to happen based on that instruction. And then down here, it's called superscalar, yeah, integer execution units and floating point, aka addition, arithmetic. Just think of it that way for now. And so that's the actual doing the work. So, and there's other parts to this which we're not going to really get to, but this is the meat of it. You have the state of your processor. You have being able to control it right here, what's going to happen, and then you have the actual execution or the work. And so those are going to be the 3 main things we're going to focus on for this class. And just for edification, all this stuff over here is usually how do you interface with other objects like your keyboard, your mouse, anytime you plug in a USB device. We're not going to go into that today because that gets can get really complicated. We're going to focus on the processor. and hopefully you can see how that can be extended to talk to different devices. All right, so building blocks for the little computer 64. You have your state, which we have memory, register files, and possibly other registers. And then you have a ROM, as well as, hey, those trapezoids. Trapezoids are multiplexers, aka you have multiple inputs, and you're going to have a selection wire to select what output you want. And then you have a box, which is a decoder, like we talked about in the finite state machine. You have multiple lines coming in, and that selects which line coming out you're going to activate. Down here we have our computation. Ooh, look, ALU, haven't seen that before. Well, let's skip that. For now, you have two pluses. Hey, those do addition. And we did talk about the half adder last time, right?
Yeah.
Yes. Yes, because we drew a circuit where you had A and B, and then your outputs were C and S, so sum and carry bit. So you have some adders as well. And you have a sign extender, we'll get to that. And for an ALU, which stands for arithmetic logic unit, you can think of that as an adder, a nander, and pretty much everything else you would need to do for arithmetic, all wrapped into one picture. So basically, we can now take a step back and think about a processor in another way, in that you can just take these pieces, etch them onto a circuit board, and now you have a processor. So we'll see if we can figure out how to do that. Oh, hey, look, there's the data path. All right, let me take a step back here. Your project coming up is going to be to implement this. This is not this LC64 data path. This is not in the book. All right, this is not in the book. This is actually in the slides. So when you have questions, you need to consult the slides to figure out how to implement it. The book, depending on which one you got, will either have MIPS or RISC-V. I don't know which one it has. Is it MIPS? People who have the book?
Yeah, I think so.
Think so? Which is not this. MIPS is more complicated than this. Although if you do use the book, it'll show you something similar to this, but not exactly the same. So the book can help you. But I'm just warning you now, when you start looking at your single cycle processor, this is the first thing you want to look at. And don't worry, we're going to be going over this in great detail soon. Okay.
This is already a lot different than the MIPS, the way the MIPS look.
It's not actually, it's different than the MIPS in the book. It's
Okay.
actually not that different from MIPS from last time.
Okay.
MIPS from last time was 32-bit. This is now 64-bit,
Okay.
which is going to be an interesting change. We'll see how well that turns out.
Boy, it's harder.
Well, you know, instead of declaring your arrays from 31 to 0, you now declare them 63 to 0. You have to have another mux, maybe? A bigger mux? I don't know. We'll find out. All right, so how do we build these control blocks? Well, first you need to have a multiplexer. You connect one inputs to out based on the selection. It's basically implementing this C code. If select is 0, out is in 1, else out is in 2. All right. Now, we need to review this stuff, because I'm sure you all have already forgotten it. Is that hard to see?
Yeah, a little bit.
Ooh, where's the eraser?
It's over here.
All right. So, what do we have? We have N1, N2. All right. And then we have select. I'm just going to call that S. And then out. Hey, so there's 3 inputs. That means there's a total of 8 possible combinations. 3, 4, 5, 6, 7, 8. Wow, that's kind of weird. All right. So inputs, N1 is 0, N2 is 0. We select 0, so the output is 0. Good. Make sure everyone's on the same page. We'll do 0, 0, 1.
0, 0.
All right. It's like we did this before. Right, because you're
Zero.
selecting the first one, so it's 0.
1.
Hey, so you'll have done this. 1, because you're selecting the first input, which is 1. And then was it 1, 0, 1,
0.
0, 1, 1, 0. So this one is signifying which one you're inputting, and then putting it, and then you just make that the output. Okay. The slides have a picture of what it looks like? Nope. What was the circuit for this? Anyone remember?
It's like, it's like a bunch of yeah, it's just like ands. It's ands, but there's not on one of the S.
So you got an S that goes to both of these, and you said there's a not on one of them?
On one of the S.
The knot that goes
so you
with
get-
an A or input one.
So the not's right here.
Yeah.
Okay. And then these two go into a
or. Yep.
into an OR. Okay.
Let me see. Yep.
Let's see if that makes some sense. Let's do this one. N1 is 0, S is 1, so that's another 0, 0, and 0 is of course 0. And then we have N2, which is 1, and regular S, which is 1, so the AND here is 1. 0 or 1 is of course 1, which is what we wanted. And I think, and this looks pretty familiar, and this will definitely be a, this will be the mux. What's the gate delay on this thing? Oh, someone erased it.
I know. The guy erased all the
Yeah, he did.
delays
He
up in the
did.
corner. It's the worst. I think it's 2 for an and.
It's 2 for an and then how many was an
Oh,
or?
I think it was 2 for the other one, but 5 is including the not.
5 including the knot.
Yeah, 5
How
including.
much? So how much is the and by itself again?
2.
2?
Two, okay.
Should be 2. And the or is 2 as well.
And then a not is an extra. Okay.
Is 1.
Yeah.
Maybe, depending on if you want to include it or not. Okay, how about a decoder? Ooh, that looks messy.
It's just the.
I'm not drawing the table for this.
You got it.
All right. Notice that is activating a line based on the input. Hey, this picture's wrong. Oh,
Yeah,
what's that?
nothing.
Wonder why it's wrong like that. All right, there we go. So you have decoder, read-only memory. We haven't talked about how you do this in Verilog, so don't worry about it yet.
It's fun.
But right now, we're just going to leave it like this. Notice it's just telling you which line to activate. All right. And the ALU. Well, notice you have inputs and you have another wire coming in. This is very similar to a MUX, but instead of selecting which input, you're selecting which function to perform. So, if input is add, then it would do an add. If input was and, then it would do an and, et cetera, et cetera. So the function is dictating which circuit to activate inside of your ALU. And I'm going to think about how, I'll let you all think about how to do that inside of your ALU module, which you will be presenting. And let's see, for LC64, that is not correct. It's really hard to clean this every time someone makes a change. All right, we have add and compare. So add adds it, and does the bitwise and compare returns 1 if it's equal, 0 if it's not. And that's actually what that equal line is sticking out. So compare is a special instruction. For other processors, there are many more functions, and you can be rest assured that there are a ton more instructions out there than just these three. But for this class, we're going to stick with these three because you can produce pretty much any program you want with these three instructions. It'll just be really slow, but at least you have all the power you need. So simple AAU doing only adds is what we call an adder. And we've talked about a half adder. We haven't gone to a complex adder, which we will soon. All right, the sign extender. Input by replicating the most significant bit to the width of the output. We haven't gotten to why this works. We will, but we haven't gotten to why just extending the most significant bit, aka, let's see, the bit 63 to 16 is just bit 15, and the rest are the rest. We haven't talked about why this works or why this trick works, but we will get to it, and I just realized I haven't told you what this does. What it does is it takes a 16-bit number and turns it into a 64-bit number. So beforehand, you can only go from, what, negative 32K roughly to positive 32K. Now you can have 64 bits, which is something like negative, what was it, 1 or 2 times 10 to the 19th to positive 1 times 10 to the 19th or something like that. Yes?
So is it just like 16 to 64, or does it have different effects based on the starting amount of bits that you use?
So the trick is, if it's positive, we haven't talked about how you encode positive or negative numbers. That's the problem. So again, I know chicken and egg, but I'm just telling you now, the sign extender, all it does is takes the most significant bit and copies it over. And that will be the easiest way. I mean, hopefully you can see that's a really easy way to do sign extension. So it'd be great if we could come up with a scheme in order to enforce that. And we will talk about that in a little bit. I am going a little top down here and not bottom up because I'm trying to give you, we really need to see the big picture at this point because we've been running around like crazy. So useful when compute is wider than the data, namely if you need more than your 16 bits. And we'll get to why this works. Foreshadowing, it's called 2's complement. All right, your register file, which is going to be a little more complicated, keeps a track of all your registers. Now, in a 64-bit machine, how wide is one register? Take a guess.
64.
Nice. All right, 64 bits wide. How many flip-flops is that? 64. I'm not trying to be tricky. Okay, so a single register is 64 flip-flops. That's it. That's how it is. 32-bit machine, a register would be 32 flip-flops. But we're doing 64, so you have 64 flip-flops. Now, in the LC, in this computer, you're going to have 32 registers inside your register file. So you're going to have 32 64-bit registers. In other words, you'll have 32 times 64 flip-flops. That's a lot of flip-flops. But that's how a lot of computers are. XA664 actually has 16 64-bit general purpose registers, plus a bunch of special purpose ones, which make it go past 32 pretty quickly. So this is not uncalled for or unheard of. So the register file is going to contain, for our design, 32 registers. Each register is 64-bit. And in other words, we need to have two read ports and one write port. What does that mean? Well, inside of a register file, we want to be able to read from 2 registers. Haven't talked to why that's the case yet. We want to be able to read 2 registers and output the contents of those registers. So if read 1 was 2 and read 2 was 4, then it would go into your register file, get the contents of those registers, and output it from out 1, out 2. The write port is saying what you're going to write to. So write 1 is the register you wish to write to, and D1 is the data you wish to write to that register. So if you want to store 64 on register 3, D1 would be 64, write 1 would be 3. And then we have a write enable bit, which is basically used to tell the register file if it's actually writing something or not. because some instructions aren't going to write to the register file, so we want to make sure that we don't accidentally write to it. And probably should have gone over this first. A register, in this case 64 bits, does have a write enable line of whether you wish to update the register or not at some point. Memory. Okay, going through, you have an address and a data in. So, in other words, if you are reading from memory, then it takes your address, goes into the address in memory, and outputs that value. If you're writing to memory, it takes the address and your data in and writes to that line, and data out is superfluous. How do you know what you're doing? Well, you have read or write bits if you're reading or writing, and you have a write enable bit in case you're doing anything. Note that if write enable is off and you have the write flag, then the memory doesn't do anything. That's just a don't do anything state, because if you disable writing and then you tell it to write, then it shouldn't do a thing. Hopefully I said that correctly. All right, so what's our machine? It's going to be called the Little Computer 64-bit. Architecture is based on MIPS, which stands for multiprocessor without interlocked pipeline stages. That means absolutely nothing to you, and that's okay. You'll understand that later. I chose this architecture for its simplicity, and that's why historically I've always taught MIPS, because it's simple. The instruction set will be based on x64, aka our 64-bit machines that we are pretty much all running. This is for a real application. It is not verbatim x64, because that would be an absolute nightmare. So it's a simplified version of x64. This is for your programming project, so you can see what Intel and AMD are going through, but at the same time give you some idea, but without going through too much pain. I've simplified it a lot, but at the same time I'll give you at least some exposure to the x64 assembly, which is going to be needed if you are in cybersecurity and you're going to start writing some, did you do buffer overflows yet or anything like that? No. Okay. In some of your future classes, you are going to need to be able to write in x64 assembly. For the rest of us, there will be times when you need to, there may be times where you need to look at it depending on your project. Okay. So like I said, we want to be able to include different types of instructions. So there are different classifications of our instructions. We have R-type, which are register-based instructions. And the three that we have are add, and compare. Namely, when you call add, it's going to take the contents of your first parameter, called register destination, add it to the contents of the register target, and take the sum of those two and push it back into the destination register. AKA, it does this. How do we encode that instruction to the processor? Well, you doing all right?
Yeah.
Just the avalanche of information? Yeah. Oh, I know. I don't know how else to give it to you simply. We'll just keep going. Don't worry, we're going to be going over this in examples again and again and again. I'm going to be tired of it, but that's okay. We're going to encode in everything in 32-bit instructions, just to be simple. Again, x86 does not use 32-bit instructions. It uses 8 to, I think it's 108-bit instructions. In other words, the instructions in x86-64 vary greatly. But we're going to stick with 32-bit to make all our lives simpler. I'm telling you that because this is not how it's encoded in x64 at all. We are doing it this way because it's simpler. The instruction is this, but the encoding is different. By the way, the opcode is the same, but the rest of it's different. So when we encode it, the opcode is going to be the first 6 bits, and that will signify what our opcode is. In other words, if these bits are 4, then it's an add. If that's not 24 because this is hex, and I can't do that in my head, but if it's hex 24, then it's an AND. If it's hex 3C, it is a compare. I chose those opcodes because those are the x64 opcodes. So if the opcode is 4, we're doing an AND. We're going to read from the register specified here, or read from the register specified here, add those two components, and put it back into the register RD. That's how we do an add. And is the same thing, except for instead of doing add, we're going to do an and. And the compare is going to be a special case. It's going to be an internal compare flag that is set to 1 if the contents of RD is equal to the contents of RS. Otherwise, it's set to 0. All right, how are we doing?
You're starting.
Oh, it gets better. So there's I-type instructions as well. These are called immediate because we're going to use the offset field. Now, because x86 is annoying, you don't load from memory or store. They're called move. So you move from register to memory, or you move from memory to register. Don't ask me why they did this. They just did. So if you're moving in this regard, RS is first. I don't know why. But you're moving from the second parameter to the first. So it's going out to that memory address, finding the contents of that memory, storing the value of that inside of RS. Now, how does it calculate what memory address? Well, it takes the contents of the RT register and add the immediate offset. So this is an actual number in the instruction, and it's going to add that actual number to RT. You okay, Perry?
Good.
Good. This part is where a lot of students get into trouble, so let me emphasize again what you're adding. You're adding the contents in the registers specified by RT. You're not adding this number. This number represents what register you go to, you read from it, and then whatever is read from that register, you add the offset. This is an actual number. This is the index into a register file. They're two completely separate things. Because RT can be 64 bits, offset can only be 16. In the other direction, the other move, it reads from RS and shoves it into RT. This is not quite right. Perfect. And lastly is a jump instruction. If the flag, that flag is what was set previously by the compare. If that flag is 1, then we need to update the PC to PC plus 1 plus offset. What's the PC? Actually, did you go over that?
I think you did.
He did. It's a program counter. It's which instruction we are currently executing, and it'll tell us which instruction we need to execute next. Yes?
Why do you have 2 chairs on the desk?
Because I was told to not sit at the teacher's desks, so I put the chairs on top so you can sit on the teacher's desk. Any other questions?
I got it.
I got it? Okay, good talk. Good talk. Notice that the first move we call a load word because it is loading from memory. So when you're looking at architecture and you want to see another example of this, Google or look in your book for LW, which stands for load word. I will sometimes call it move L to signify that you're moving a load. The other one is called an SW, or a store word, because you're storing out to memory. You're storing the value to memory and not loading it from memory. All right. So those 6 instructions plus 2 more, or actually those are it. Those 6 instructions are actually enough to give us a full processor that is actually theoretically just as powerful as your 64-bit machines we have. Obviously, it's going to be nowhere near as fast, but it does give you all the power needed. All right, so we look at this data path, and let's do the add instruction, and then we're going to stop, because hopefully this will make some sense. So the add instruction, you have add RD/RS, where your destination is equal to the contents of the destination register plus the contents of the source register, and then we're going to increment the program counter. So let's do add 3, 1. What does that mean? Well, look at this. we are going to send, notice from instruction memory is where we are reading the instruction. So you can kind of think of it as this is where the path begins. It's up to you, but this may help. So the instruction comes from instruction memory. Well, it's going to forward 3 to the register file and 1 to the register file, which will output the contents of register 3 and the contents of register 1 down here. Because of our decoder, hey look, these decoder is our lines to our muxes and our enable bits, which will help us determine what should be what. That should be a 0 right there. Well, it kind of disappeared. It's an orange 0. So this is a 1 here to signify you take the 1 element, aka the second input, and you forward that to the ALU. So you are forwarding the 2 values read from the register value to the ALU. We'll say 0 is the add, so then an ALU would add it, send it back here, which goes to this mux, which is saying that you want to read from this input. Why do we have 2 muxes? Well, one's coming from the ALU, the other's coming from data memory. In other words, this mux is determining if we are writing to the register file from the ALU or from the data memory. In other words, put in the reverse order of what I just said, if we are trying to send a piece of memory to the register file, we may want to send the ALU or send memory. How do we determine? We use the mux to determine which memory or which output is being sent to the register file. I just said the same thing completely differently. So that mux says we're going to read from the ALU, forward it to the register file. This mux, which should be a 0 from our decoder, signifies that we want to forward this value, which is where we're writing to. The reason for that is other instructions may have a different write value. So we're going to forward 3 from where we're writing. We're going to forward the data from the ALU to the register file, and then that will complete add. A couple of other things I did not talk about though. Notice that these bits are your opcode, which is going to that decoder we talked about. In our finite state machine for the coin machine, we had a 5x32 decoder. This is going to be 6x64. Why? Because we have 6-bit opcodes, so the inputs are 6 different wires. And then by 64, because there's 64 different lines that can pop out of here. Don't worry, Verilog is going to have a simple way to implement this. And then that'll activate which lines we come out, just like in our finite state machine. Up here, add does not mess with the program counter, so we're going to add 1 to PC and make the program counter go to the next value. The program counter signifies the address inside of memory, so by adding 1 to the program counter, we are signifying to go to the next instruction that is inside of memory. All right, I'm going to stop here because we just went from probably the finite state machine, which sounded great, to what's going on. How are we doing? We will review this again, trust me.
There's so much wrong with that I just
There's so much wrong with it.
do not even know where
No, this actually works.
Well, yeah, it works. But I don't even know how to begin with this thing.
All right, well, we'll get to it a little more. All right, let's go look at Scrum 2.